During the project at FZI, we developed a tool that is called SIMULTime. SIMULTime is a timing analysis tool that produces early timing estimations for the execution time of a program considering multiple hardware platforms. Non-functional properties, as the execution time of a program, are essential in hardware-software coevolution. SIMULTime is a measurements-based timing analysis tool. Measurements are extracted directly from the hardware platforms, and, differently from static analysis, they allow modeling complex hardware mechanisms that nowadays are commonly included in processors and platforms, as for example, multiple-level cache memories, out-of-order and speculative execution, branch predictors, and others. Analyzing the timing traces and consequently generating a timing database, SIMULTime can produce fast and accurate timing estimations via code simulations. The simulations are based on the LLVM IR code. The IR code is the compiler internal representation of the software program, and it is hardware independent. This property allows simultime analyzing in parallel multiple hardware platforms, and therefore considering the hardware evolution. Furthermore, the simulation considers different input data, for instance configuration files, that enable at runtime parts of a software program, and evolving it. Finally, we also developed a Matlab Simulink extension for our tool. This extension allows evaluating the timing effects of a Simulink model considering its execution on a target processor. The timing effects visualization is directly included in the Simulink simulation. SIMULTime combines tools from the LLVM compiler infrastructure and analysis tool we developed internally at FZI. The tools are mainly written in C++ and Python. Currently, the only operating system supported from SIMULTime is Linux. Tools integration for SIMULTime is possible. In fact, SIMULTime can analyze C++ programs in input, generated directly from developers or from any other automatic tool. Timing traces are fundamental for our analysis. These traces can be directly extracted from the hardware or from an accurate simulator. SIMULTime supports a well-defined trace interface. It is possible to extract the timing information from our tool as raw text data or in a structured timing database that can be imported in Matlab Simulink. This is the SIMULTime workflow that shows the main activities required for generating fast and accurate timing estimation. Initially, our tool expects in input a C++ application that need to be compiled. The compilation relies on some LLVM tools, as for example, Clang, OPT, and LLC. The compilation phase produces two outputs. The first output consists in one hardware-independent IR file that is the result of the front-end and back-end compiler phases. The second output is represented by multiple executable binary files. These are generated continuing the compilation with the back-end and the linking phases. One executable per hardware platform and hardware-dependent compiler optimizations is generated. Thereafter, two sub-activities are executing during the analysis phase. The first activity generates one timing database per binary executable file, relying on the timing information contained in the provided timing traces. The second activity produces the necessary IR to binary mappings to utilize during the simulation for querying the timing databases. These mappings are necessary because the timing traces are based on the software binary representation, but the simulation are executed at the IR level. Therefore, a connection between the IR simulation code and the timing database to query is necessary. Both the compilation and analysis phases has to be executed only once. Finally, multiple simulations can be executed for producing the necessary timing estimation. The simulations are based on LLI, an LLVM tool that directly executes IR code. Simulations can be executed via the interpretive execution engine or via the faster just-in-time execution engine, providing in input to the simulator one or multiple timing databases, the IR to binary mappings, and a configuration file that contains the program input data, it is possible to start the simulations for producing the timing estimations. Attaching multiple timing databases to the simulators allow accessing multiple hardware platforms in parallel. Our Matlab Simulink extension allows generating C++ code producing one function per component in the model. After the simultime analysis, the timing estimations are back annotated directly on the model, and the enriched Simulink simulation can be conducted considering the timing effects of running the model on a target hardware platform. Now, we show how to produce fast and accurate timing estimation with SIMULTime and this Matlab Simulink extension with two examples. As first example, we evaluate a C application composed of a monitor unit. In particular, in this example, we are interested in showing two main SIMULTime capabilities. First, the analysis support for runtime variability in the code, and second, the possibility of assessing hardware evolution by analyzing multiple hardware target platforms in parallel. This is the monitor unit application written in C. Depending on the criticality level of the sensors, different actions are taken during the program execution. This is what we call runtime variability. The runtime variability is managed by a configuration file that can be stored in memory, volatile or non-volatile memory. As a first objective, we show how SIMULTime can provide multiple timing estimation for different configurations. For this purpose, SIMULTime needs to execute the analysis phase only once. Thereafter, the extracted information can be utilized in multiple simulations. For this specific example, we are going to analyze a platform including a Cortex R5 processor from the ARM family. The traces are extracted directly from the target utilizing the Lauterbach Trace32 tracer, a non-intrusive tracer. On the left side window, it is possible to recognize the C program, mixed with its binary representation. On the top right instead, there is a window that allows easily modifying the configuration parameters. This feature is helpful in tracing the program with multiple input data. After the program is executed, the timing traces can be extracted and later analyzed. Analyzing the extracted traces and applying a REVaMP function, abbreviated form for virtual inlining and virtual unrolling function, it is possible to generate a timing database that is specific for the program, the hardware target platform, and its hardware configuration. Configuration means enable hardware resources and applied hardware-dependent compiler optimizations. In order to produce accurate timing estimations, it is necessary to trace multiple configurations and visiting different paths in the control flow graph. After the timing database, we need to generate also the IR to binary mapping file. This task is fully managed by our scripts, and they ensure an exact map. In this example, we are going to run our simulations relying on the faster just-in-time LLVM IR execution engine. For this reason, we first need to instrument the IR simulation code. The instrumentation inserts some function calls that forces the simulator to query the attached timing database relying on the IR to binary mapping. The interpretive execution engine does not need to instrument the code. The IR to binary mapping is resolved at runtime. Once the annotation is completed, the simulation can start. The timing database and the simulation code are given in input to LLI. LLI determines the control flow path, and depending on the visited basic blocks, it fetches the relative timing information from the timing database. At the end of the simulation, the timing estimation is provided in output. Multiple simulation can be executed by modifying the data configuration. In this case, the configuration is directly included in the IR code. We change the criticality of the first two sensors and we run a new simulation. The timing estimation is then updated. The spreadsheet shows the estimation's accuracy. We compare the target timing values with our estimations. In both the cases, the estimations are highly accurate. This result is the consequence of a proper coverage of the control flow graph while tracing. Finally, we show that SIMULTime supports the hardware evolution, allowing accessing in parallel multiple hardware platforms. For this reason, we repeated the previous described steps for a second platform that includes a Cortex-A15 processor. This second platform is more powerful, and it is consequently faster. Providing an input to LLI information for both the platforms, SIMULTime produces two timing estimations. The first one is the timing estimation for the execution of the program on the Cortex-R5 processor we have already seen. The second one is the timing estimation for the Cortex-A15 platform. Additional platforms can be analyzed in parallel. We are now going to show a second example, considering the Matlab Simulink extension. In particular, we show the complete workflow that allows evaluating a Simulink model considering the timing effects due to its execution on a hardware target platform. This is the Simulink model we are going to analyze. It contains two different types of components. The green components are software components. In contrast, the gray ones are physical components. We are interested in analyzing via SIMULTime only the software components. The system component may contain subsystems as well. We are going to analyze all of them, including the subcomponents. The Simulink timing analysis starts by annotating the model. In particular, during the annotation, it is necessary to specify which one of the blocks in the model is the software component. Then, the hardware processor to consider during the analysis. Thereafter, it is necessary to specify the hardware processor configuration. That means which physical resources to enable. Here we enable both the cache memories and the branch predictor. Finally, it is necessary to specify the compiler optimization to apply during the compilation phase. After the annotation, the code is generated and compiled. We utilize the Simulink target language compiler to produce a C function per element block. Thereafter, the timing traces are extracted directly from the target platform and SIMULTime executed. SIMULTime produces as output a timing database containing timing information to include directly on Simulink. Once the timing database is imported, two main activities are executed in the background. First, a functional equivalent model is created. Second, the new model is back annotated with delay blocks. A delay block is a library we implemented that forces the Simulink simulation engine to consider the timing effects due to the software execution on a hardware platform. The back annotation activity inserts a delay block at the output of every subsystem in the model. Inside the scope, the blue curve represents the enriched model behavior. Finally, we compare the native Simulink simulation results with the enriched results we obtain considering the timing information produced by SIMULTime. The original Simulink output is plotted in black. Instead, the timing-enriched results are plotted in green. The chart shows the differences between the simulation behaviors. The timing effects force the model to be less reactive. Zooming into a convenient interval, it is possible to highlight these differences. During the project, SIMULTime has been developed completely by FZI. Currently, it is not open source, but we can provide demos on request. In case you are interested in a demo, please contact Alessandro Cornaglia or Sebastian Reiter. Finally, we want to thank Shakib Hassan for his support in implementing the SIMULTime Matlab Simulink extension.